This is the last lesson, nuclear spin and magnetism. Nuclear spin and magnetism. So when the nuclear is moving, so nuclear is usually moving around the angular movement. So this is we call a spin. So this nuclear spin is this also produce a magnetic movement. So this is the nuclear. So this one usually moving in this spin here. So this is moving. So moving it can produce a magnetic moment. So this is we call a nuclear spin and the magnetic moment. So they are the force between the neutron, nuclear proton, and the neutron. So this is for the in the nuclear in the center. Is we call it this is the nuclear. Nucleus it includes a positive proton and then zeros are neutron. The positive is a proton and zero is a neutron. So those neutrons and protons are charged by the electron. So this is the E is an electron. So positive proton and the negative neutron, they are charged by the negative electron. So this is for the force between the proton and neutron is the force binding force. So that this is a positive proton and a zero neutron. So they got the binding force. So this is a binding force. The force between the positive and the negative zeros and neutrons is the binding force. So this binding force is a strong force. This is we got it. The binding force is a strong force. So therefore, when we are taking out the proton from the nuclear, it needs a lot of energy. So the separating the electron, proton from the neutron, it can produce a lot of energy. So this is what is nuclear. Normally, we can taking out the proton by collecting the one nucleus to another one. So this is the nucleus collision. By nuclear collision, it can produce the highest energy level. This is for the force between the proton and neutron. This is the binding force. This is a strong force. The nuclear force that binds the neutrons and proton is a secondary or spillover effect that binds the quarks together to form the proton and the neutron. So this is for the nuclear force. So we can calculate the nuclear density. So what is the density of the nuclear? So in this case, the density equation is a rho. Rho is equal to the formula A and divided by the 4 by R cube. So A is the nuclear containing the A neutron. The mass of the nuclear containing the A nucleon. Nucleon means this is also included the nucleus and the electron together. So this is for the mass of a nucleus containing a nucleon. So this is the AM. And the I is equal to the radius of the nucleus. Radius of nucleus. So R can be calculated. The formula is R0. I is equal to R0 into A power 1 time. That's the equation. So therefore, we can substitute. So then we will so R power 2 is equal to R0 power 2 into A. So therefore we substitute. So the rho is equal to the AN divided by 4 by touch by R power 2 is equal to the R power 2, R0 power 2 multiplied with A. So this A will be cancelled. So this is the mass of the atom divided by 4 by touch by R0 over 2. So this equation. So in this case, we can write down as mass of this atom. Mass of the atom is equal to the 1.67 into 10 power minus 27 kg. So we substitute here 1.67 into 10 power minus 7 kg. And 4 by that minus 3.1416 R power 2. So this is for the nucleus are radius. So our 2 is a 1.2 into 10 power minus 15 meter. 1.2 into 10 power minus 15 meter power 2. So by solving this one, what you got the thing is 2 into 10 power 7 kilogram per meter cube. So this is for the density of nucleus we can calculate by this way. So the next problem is what is the binding energy per nucleon for 120 SN. So firstly we write down the here 120 SN are nucleus. So it includes 50 separate protons. Plus 73 neutrons. So that 150 SN nucleus contains 50 separate protons plus a 70 separate neutrons. So we can write down the equation. In this case, the energy produced by the electron is equal to the 50 into mass of the nucleus into the C square plus 70 into the mass of the neutron. So mass of the neutron and the C square and minus m SN C square. So this equation. So in this case, the mass of the atom is included. This is the mass of the proton and mass of the neutron and the whole mass and the C square. This is the velocity of the light. So therefore we can write down here and then is square root is 50 into 1.00 into 825 U into C square plus 70 into the 1.008665 U into C square minus this is the 119.902197 U power C square. So by solving this one, what you got the thing is 1.095603 U power C square. So this is the C square is electron volt. Can also be calculated. So this is the 1.095603 U multiply C square. Also the equal to the 931.494013 mega electron volt per unit. So U means a unit. So by solving this one, what you call the thing is 1020.5 mega electron volt. So this is for the 120 SN nucleus. It can produce the force 1020.5 mega electron volt. Can be that produced. And therefore, we have to calculate the binding energy. So binding energy. So binding energy is this is for the binding energy chain divided by area. So this is the binding energy density. So this is the binding energy chain divided by the number of atomic number. And therefore the binding energy chain is we can see the 1020.5 MeV divided by atomic number is 120. So therefore the 8.5 mega electron volt divided by nucleon. So the binding energy density or the binding energy per nucleon. So the binding energy chain divided by the atomic number. So you got the 8.5 megavolt per nucleon. So this means 120 SN are nuclear. So this is the thing that this nucleus can include the 50s are proton and the 70s are neutron. So the protons are the energy can be calculated mh into c square. So proton mass and the molecular light square. So the proton mass is at 1.00825 unit, and neutron mass is at 1.00865 unit. So that we substitute, and also the mass of the atom is at 119.902.197 unit. So by solving this one, what you got the thing is 102055 mega electron volt. So this is for the whole nuclear. The nuclear energy by nucleon can be calculated. So this is a total binding energy change divided by the atomic number. Atomic number is 120. So that we got the 855 mega electron volt by nucleon. Another one is a radioactive decay. Radioactive decay is when the nuclear activity happens, so nuclear activity is neutralized. So this is time required to disappear the nuclear activity. This is the nuclear radioactive decay. So radioactive decay rate can also be calculated. So this is the R. The next one is the radioactive decay. So radioactive decay is times are required to eliminate disappear the nuclear activity. This is the radioactive decay. So radioactive decay can be calculated. So radioactive decay rate is R. So R can be calculated. So this is equation minus Pm by dt or the lambda n0 e power minus lambda t. So this is the equation for the radioactive decay. So the R is can also calculated. R0 is the e power minus lambda t. So this is for the radioactive decay rate. So can be calculated by this equation. So in this case, the lambda is a wavelength, and so this is for analysis disintegrations are constant or decay constant. Decay or disintegration constant. So decaying of the disintegration of the decay constant is the lambda, and this is for the initial time. This is the initial time. So this is for the calculate minus the radioactive decay equation. The equation is that once equal or the 1 BQ can be calculated as 1 decay per second. So this is for the rate of the decaying. So this is for the full nuclear energy to reduce to the half. So this is for the T half. Ti is equal to tau into ln2. So tau is the time constant ln2. So this basically you can calculate the half, T half. T half is the half of the nuclear light. This is for the table. Table follow the measurement of the decay rate for the 128I. 128I is a radioactive iodine. So 128. So radios are nuclei. So this is often used as a medical as a tracer to image to measure the rate at which the iodine absorbed by the thyroid gland. So this is what iodine is utilized by the medical treatment. So the hematocrit are decaying. Iodine radioactive like 36 minutes. 1/4. 3 minutes. Time is a minute. So we can measure up to the 200 18. So this is a 0, 50, 100, 150, 200 around here. And this is a step from the 600. The number of curve per second. Number of curve per second can also be calculated. So this is for the vertical line 2, 4, 6 like this. So in this case, our curve is a step down here. We can draw it as a graph. In this case, this graph we have to draw a graph. In this case, we have to use a logarithm scale. So this case, we have to utilize a logarithm scale. So therefore, there's ln r is equal to this is called ln r0 e power minus lambda t is equal to the ln r0 plus ln e power minus lambda t. So that becomes ln r0 minus lambda t. So this equation. So This R0 is that we can put the here. Sine R0 you can put, you can draw the graph. So this graph you can draw the graph with this one with the graph. The count horizontal graph. This is a straight line graph we got. Okay, this straight line graph we can measure. So this one is a 6.2, and this one is a measurement. This is 225. So we can measure the slope. Slope is equal to that going down. So the final point is 0, original point is 6.2. 0 minus 6.2, and final point is 225 minutes. Origin point is 0. So this one will be this minus 0.0276 per minute. So we got. So there will be this slope is equal to this equation. So this is this slope is a minus lambda. Minus lambda is a minus 0.0276 per minute. So therefore the lambda is equal to 0.0276 minutes or 1.7 hour. So this one is then the T-hub also can calculate it. T-hub is equal to the equation tau into ln2. So tau is equal to 1 by lambda into ln2. So that ln2 divided by lambda is 1 by 7. So 1 by 7 is lambda is 0.0276. 0.0276. So the ln2 divided by 0.0276, you got 25 minutes. So this is for the half time is decay is 25 minutes. Okay, the next one is alpha decay. Alpha decay means when is a nucleus undergo the alpha decay, it transforms to a different nuclei by emitting the alpha particle. So when the nuclei is going to the decaying the radioactivity is going down. In this case, it can produce the alpha particle. For example, uranium U-238 making the alpha decay. So original 238U will produce the 234TH and the 4HE. So this is for another two metal to two atom. So TH atom and the helium atom they are producing. So this is for alpha uranium 238U are decaying. Nuclear decay, so it can produce energy. So the energies are released in the decay process. Can be calculated. The energy released in the decay process. So the energy released in the decay process can also be calculated. This is for the heat. Q is equal to F initial mass multiplies light velocity square minus final mass multiplies light velocity square. So this is for the produce. So this is for the disintegration energy is Q is equal to initial mass multiply the light velocity square minus the final mass multiplies the light velocity square. So this is for this Q is the energy disintegration energy. Disintegration energy. So when the nuclei is decaying, it produces energy. This energy can be calculated by this equation. So this is for the original nuclei is uranium 238. Uranium 238 is decay. So in this case 234TH and the 4 H's will coming out. So in this case we have to calculate the energy released. So energy release formula is Q is equal to MIC square minus MSC square. So this is MI is the initial mass multiplied with the light velocity square minus MA is the final mass multiplied light velocity square. So we calculate. So this is Q can be calculated. MI initial mass is here 238.05079 U in C square. So that's 238.05079 U into C square. Minus final is this one 234.04363 and so 4H is 4.00 So therefore we write down the thing 234.04363 U plus 4.002 60U into C squared. So by solving this one, the what we get is a 0.00456U into C squared. We got. So the ones are C squared. This is for the ones are light charge velocity. It can produce a relevant 31.494013 mega electron volt per unit. So this is for the light velocity. When the any particle is moving at the light velocity, it can produce as energy. The energies are retained by the any particle moving at the light velocity is 931.494013 mega electron volt per unit. So this is a 0.00456. You multiply. This becomes 931.494013 mega electron volt per unit. So by solving this one, what you got to say is 4.25 mega electron volt. So therefore, when the uranium 238 says decaying, so it can release the energy 4.25 mega electron volt. This is for energies are released by the nucleus are decaying. How is the beta decay? Beta decay means that it can emit the electron. Eliminate electron on the positron. So this is a positron, is a positively charged particle. So positively charged particle by the electrons are emitted from the nucleus. This is called beta decay. So there are two kinds of decay. One is the alpha decay, it can emit the alpha particle. So this is the alpha decay. Beta decay is it emits the electron or positron. So this is the beta decay. So two kinds of decaying happening for the nucleus. This is beta decay. For example, phosphorus. Phosphorus is a radioactive phosphorus, P32. P32 is this is the atomic weight 32. When the phosphorus is decaying, so it can happen as sulfur. Sulfur is atomic number 32. Sulfur 32 plus electron. It can also emit the electron plus a neutron. So V is a neutrino. Neutrino is a neutral particle with very small mass. So the phosphorus P. So radioactive phosphorus is decaying, it can happen as sulfur 32 plus electron plus neutron V. Similarly, the copper 64 is decaying, so it can happen as nickel and like 64 plus the electron plus V is a neutrino. So this is called a beta decaying process. Beta decaying process is once particle is decay, so that it can produce as an electron and another particle and as a neutrino. So this is called a beta decay process. Radioactive dating. Dating means that we can measure the light. So how we can measure means that the content of the carbon. The content of the carbon, the radioactive material in the rock can be calculated by measuring the content of the radioactive materials in the rock. We can notice how long the rock. So this is the age of the rock can be measured. So the decay of the very long light nuclei can be used to measure the age of the rock. The poison is radionuclide. So this is the potassium. Potassium is radioactive. So this is the decay. After the decay going down, the radioactivities are decaying. So it can finally become the argon. Argon is stable. So no more nuclear activity. So it will take the 1/2 into 10⁻⁹ years. So from the potassium going down to the argon, potassium is radioactive, and going down to the argon is no radioactive so gas. So it can take the 1/2 into 10⁻⁹ years. And therefore, based on this principle, Nk is equal to the age or original content multiplied with e power minus lambda into t. So this formula. So by using this formula, lambda is equal to this is for the constant. Decays are constant. Decay constant original content of the radio activity nuclei, and then we can know the finite content of the nuclei. So this is the time. So this is the number of years requirement. So the time requirement. So by solving we can know the age of the rock. So therefore, we can utilize the radioactivity dating in the astrological process. For example, when we dig the ground, so sometimes skeleton or there is a tool used by the storage. So when you take out the tools and materials are used by the storage, and we measure the radioactivity. How much radioactivity contents are included, and then we can use the formula to calculate, so that we can know how long it has been dig into the ground. So this is the way that we utilize the radioactive dating system. In this problem, the gamma rays are close. Gamma rays are dose of the a gamma ray dose of the 3 GY is a letter to half the P by 8 to 8. So this means that nuclear rays. Nuclear rays are the radioactive rays are very dangerous. So people can die by the radioactive rays. So the 3 GY energy levels gamma ray is a letter to the half the P by 8 to 8. It's the equivalent energy where absorbed as a heat, while the rise in the body's temperature. So in this case, 3 GY is 3 joules per kilogram. So we can calculate the body temperature. So the temperature change can be calculated. Delta T is equal to Q by N. Heat divided by mass divided by the light velocity is C. So this is the calorific value. So C. So in this case, the Q bar meter is equal to 3 joule per kilogram. So 3 joule per kilogram divided by the calorific value is 4180 joule per kilogram Kelvin. So by solving this one, that will be 0.7 milli Kelvin. So this means that no one can feed any heat because of this is a 0.7 milli Kelvin. So temperature is only very 0.7 milli degree Kelvin increase. So that no one can be notice about the radioactive because of the radioactive their temperature is very low. So that no one can feed, but this is already got this rays later time that people will suffer the cancer and they can die because of those radioactive rays. We can examine the nuclear, the model of the nuclear, how the nuclear is composed. That we have to determine the compositions of the nuclear. So firstly, is a model with a qualitative model. Qualitative model is examined by the Bohr. So it has a nucleon. Nucleon means the nuclear. Nucleus are containing the positive proton and zeros are neutron. So this is a nucleon. Nucleon means the nucleus containing the positive proton and then zeros are neutron. So this is positive nucleons they are moving around the nucleus at the randomly. So that they have the nucleus. So they are interacting very strong with each other. In this case, all the nucleon means the nucleus inside the matter atom. Their nucleus is moving from the one place to another place. So they got a very strong force between the one nucleon to the another nucleon. So this is what is a qualitative model. Qualitative model is this is a compound nucleus. It is containing the electron and the proton and the neutron. They are moving in the randomly in the atom, so they are making the interaction to the very strong interaction to the each other. So this model is a qualitative model. The nuclear model, the nucleons are moving around in the nucleus at the random the image to the interaction with each other. So in the nucleus the nucleons they are moving around. Moving around, they are making the interaction. So the nuclear reaction forming this is when the projectile enters to the target nuclear A. So it can form the compound nuclear field. So this possesses excitation energy. So this excitation energy decay. So decay is another two particles happen. Y and P particles happen. So initial 8 nuclear is a hit with the projectile A. So it can happen that excitation compound nuclear speed with the excitation energy. So this excitation energy compound nuclear speed is a decay to the another format. So there will be another two particles, Y and P particles happen. So based on this formula, we can study the neon. 20 neon nuclei. So this 20 neon is we combine with a 15 oxygen plus alpha particle and 19 fluorine plus positrons particle and 20 nickel plus plus the gamma rays particle. So when they make a neon like 20 neon plus gamma ray particle. So output can be that 18 fluorine plus 2 hydrogen, 19 neon plus N particle, and 17 oxygen plus 8 helium particle. So those are coming out. So this is the 3 formation mode input, and this is the 3 decay mode output. So this is for this body is a nuclear reaction format. So in this case, this is for the combined model. The combined model, the nuclear in which is small number of neutron proton. So nuclear is usually exists with the neutron and proton. The exist outside the core of the closed shell. That contains a magic number of the neutron and proton. This means that in the nuclear here, this is for the nuclear. So outside the nuclear shell, there are another state. The electrons are moving around the nuclear. They also possess the energy the electrons they also possess the appropriate energy level. Depending on the orbit number, they also possess the energy level. The outside the nucleon occupy the quantized state in the position well accepted by the central core. So this is the central core. All the central cores are those are the nuclear reaction force between the orbits, rotating the particle, the volume particle, and the nuclear. So those are their potential energy is determined by the nuclear. So the outside neutron interact the central core. So the nucleon they interact with the central core. So they are interacting so the central core will be the deforming, and also it can also happen the vibration. Vibration and deforming happen. So it can also produce a tidal wave motion. So those nuclei are moving because those nucleus are moving around. Their force are interact with the central nuclear. So because of this, their interaction, central nuclei is deforming. Their side is changing. Their side are changing, and also it can happen as a vibration. So this vibration happening, so that model is a collective motion model or the combined model. The nuclear core, they are moving around by the nucleon. Nucleons are moving around, so they are making an interaction with the central nuclear. So they are force between happening. This happening is similar to the tidal wave or the movement or vibration. Those are the energies. They also produce the energy. So this model we use as a collective model. So those electrons are moving around the nucleus. These are possess electromagnetic force. Electromagnetic force or the Coulomb force. So those electromagnetic force are also can produce as an energy level. Energy level is a Q is equal to mc square equation. So those electrons are possess the energy level. The energy can be calculated by the equation Q is equal to the mc square equation. So any matter can release energy. So now we draw this table. So the matter released by the energy released by the 1 kilogram of the matter. I give you in the table. So this is for us how the nuclear energy released. Electrons are in the atom by the electromagnetic Coulomb force. So this means nuclear. So electrons are moving around the nuclear. So they are in the atom. So electrons cannot move out. So they are normally the nuclei is attracting the electron. So this electron is electromagnetic force. The electromagnetic force produced by the nuclei is attracting the electron. So therefore the electrons are moving inside the atom, but they are not moving outside of the atom. The electrons are held in the atom by the electromagnetic Coulomb force. It takes only a few electrons to pull one of them out. So if you want to take this electron out from the atom, you have to produce the appropriate electron volt. So if electron volt is you provide so that the electron will be coming out. And in the meantime, the neutrons are held in the nuclei by the strong force. So this is a difference between the electron and the neutron. The nucleus cannot be destroyed. You can take out the electron easily because the electricity, these electrons are moving from the one to the another place. A little body you provide, electron can come out. But the nucleus, you cannot destroy the nucleus because nucleus is very strong binding force. So if you destroy the nucleus, this means that a lot of energy is required. Destroying the nucleus means when the nucleus is breaking out, it can produce a lot of energy. So a lot of energy is the equation Q equal to the delta mc square equation. So this is the mass, this is the light velocity. Light velocity is 3 into 10 power 8 meter per second. So a lot of energy can be coming out. So neutrons are held in the nuclei by strong force. It takes a few million electron volt to pull one of them out. So the fact that the few million is reflected in fact that we can extract a few million times more energy from a kilogram of uranium than we get from a kilogram of the coal. So this means that kilograms of uranium are very easier to destroy the nucleus, so that it can produce a lot of energy can be coming out from the destroying the nucleus of the uranium. So in both the atomic and the nuclear energy burning, the release of energy is accompanied by the decrease in the mass. So that when you are destroying the nucleus, so the energy will be released and mass will be going down. So the energy released by the 1 kilogram of the metal for the water are 15 kilometer water flow. In this case, the time taken is 5 seconds. And so the coal, when the coal is burning, to burn the 1 kilogram of the coal, so you have to take 8 hours. And enrich UO2, uranium, and the oxygen. So in this case, the fission in the nucleus reactor. So the whole 1 kilogram burn out is needed 390 years. And uranium 235, complete fission, so 3 into 10 power 4 years. Hot deuterium gas, so the complete fission 3 into 10 power 4 years. Metal and the antimetal complete annihilation, so the 3 into 10 power 7 years. So this means that it can take a lot of energy. So the 1 kilogram of this uranium can produce a lot of energy. So therefore that nuclear energy is very powerful on the wall because of the small amount of this uranium can produce a lot of energy according to the equation Q equal to the delta M into C square equation. Okay, the next way is the nuclear fission. So normally it's thermal neutrons. Thermal neutrons are very slowly moving neutrons. They are the thermal equilibrium state. Normally the thermal neutrons are very slowly moving with the thermal equilibrium state. So they within the room temperature. When those neutrons are they are colliding. So when those are colliding, so the nucleus absorb the thermal neutron. When the nucleus absorb the thermal neutron, so it can produce a highly excited nucleus. So this highly excited nucleus is split into the two portions. So there will be two neutrons coming out. So this is what we call the nuclear fission state. Normally those nuclei is absorb the thermal neutron and they are split. When they are split, they produce the two neutrons, so that at the time of the separation, so it can produce a lot of energy. So this is what we call the nuclear fission process. So the next one is the nuclear fission. So thermal neutron is slowly moving neutrons in the thermal equilibrium with the surrounding matter at the room temperature. When the uranium 235 is bombed out with the thermal neutron, a uranium 235 nucleus absorbs the thermal neutron, producing a compound nucleus uranium 236 in the highly excited state. Normally the uranium 235 is a normal uranium, but when they are the compound with the neutron, thermal neutron, so it can become a highly excited state, highly active state, uranium 236. It is this nucleus that actually undergo the fission. So in this case, that uranium 236 will split into the two fragments. So the fragments become hesium, so the 140 hesium, and the thorium Z38. The two will be coming out as a fission element. So they are fission is a very high power. So by this is it can produce a nuclear energy. So therefore we write down the equation for this here. 2's are 35 are uranium plus neutron. This is a nucleus 235 and collide with the neutron. Carbon neutron, so it can become a 8 metal and a white particle and a 2n. This is the energy neutron level. So this is the coming out of this because the nucleus fission model. For the neutron and the uranium 236 they are collide. So then we the either and split into a 2 neutron. So this is for the nucleus fission model. 235 and neutron combination produces a uranium 236. So this is a nucleus fission equation. This is for the nucleus fission process. So firstly are the uranium 235. So they combine with the 133 neutron. So they become a nucleus uranium 238. So this is the first fission happen. So in this case, it can produce a 13705 neutron. So the sun neutron will be decay with 1 of the 3 and the 5 neutrons are enter into the moderator. The moderator is that those neutrons are nuclear fissions, those neutrons are very fast, so that they are simply need to be moderated, need to be slowed down. In this case, I'm going to mixing with the other material. Mixing with the other material, the fission process will be slowed down. So therefore, the mixing with the other material is very important. In this case, we have to put the uranium bar and also put the boron bar. So we put in the boron bar, the uranium bars are their interaction. The nuclear fission need to be slowed down by the putting the boron bar. So therefore, this bar here, depending on the position of the bar, the nuclear process is slower and faster, depending on the how much you put into the bar, how many bars are there that you insert or their bar distance, their penetration distance, depends on the nuclear reaction. So therefore, we have to utilize a moderator. Moderator is important because without moderators, we can't control the nuclear reaction. Nuclear reaction can't control the nuclear reactor can be explode. And therefore, the moderators are there. One of the 3 and the 5 neutrons can be slowed down and it can reduce to the 1 of the 170 thermal neutron. The some of the neutrons they are captured by resonance, some are captured by the thermal process. So the net is the 1 of the 5 thermal neutron. So those are 1 of the 5 thermal neutrons are with the thermal leakage. So that 1 of the thermal neutrons they enter into the uranium 235. So this is for the nuclear reaction process. So when the first nuclear is they are moving, in this case the first fission process it can produce the heat. So the heat, so this is the heat that produce the water. Water is passing through, so the heat produced by the reactor heat the water. So this is the heat that produced by the water. So this water hot water. Hot water also passing through the another water line. So this is the primary loop. Primary loop very hot water. Radioactive water. Radioactive water there is a hot there. They heating the cooling water. The cooling water is passing through. So this cooling water becomes the steam. So steam that dry this turbine. Turbine covered with the generator. So that it can produce outside electricity. So those things are the cool down by the steam cooling part. So this part is a water part and this part. The cooling water part and this part is very important. Once the those parts are shut down or damaged, so we can control the nuclear reactor. So in the Fukushima nuclear power station happens this part, the circulating this one, this is the turbine system, cooling water system, this part is the stop-it. Stop-it is so hot, very hot, the temperature cannot be controlled. Cannot be controlled so that it can make the nuclear leakage. Nuclear leakage happens. So this nuclear leakage has to cool down. The only thing cool down is that they use the external water to cool it out, nuclear reactor. But in any way that those nuclear water they are leaking, they are coming out. Those things are also the containers the radioactive radioactivity so that around 30 kilometers circle area that no one can go in there because of the radioactivity. So this is called a nuclear process. Nuclear process is no water parts are very important thing. Once the water parts are shut down, they are damaged. In this case, we can control the temperature of the nuclear reactor so that four nuclear reactor things are coming out. Those things will contain it. Especially this circuit is a radioactive circuit. So radioactivities can spread to the surrounding. So this is the danger of the nuclear system. Okay, so this program is that electric generating station. It's a powered by a pressurized water nuclear reactor. So this is a pressurized water nuclear reactor. So this nuclear spin produce the spin that driving the turbine. So water nuclear reactor. So the thermal power produced in the reactor core is 3,400 megawatt, and so this is the reactor core is the thermal energy, so 3,400 megawatt. So the energy, electrical energy output is 1,100 megawatt. So this is the electricity. So the pure charge is 8.4 into 10 power 4 kilogram of the uranium in the form of uranium outside. It is a distributed amount of 5.7 into 10 power 4 QR. The uranium is enriched to the 3% uranium at 235. So what is the station efficiency? So uranium need to be enriched 3%. 3% enrichment is it can only produce the nuclear power, nuclear energy, but it cannot produce the bomb. The bomb production is more enrichment. The 50% enrichment, 100% enrichment at the time that it can produce the nuclear bomb. And therefore, in the nuclear power station, the enrichment of the uranium is tightly controlled by the NAE. NAE is usually control the enrichment. So it's any country who are signatory of the NAE is nuclear no substance territory. So in this case, they have to observe accept the IAEA inspection. So this is the uranium enriched to the 3%. So what is the station efficiency need to be calculated? And these effort rates are two fissions even order in the reactor core. And C, effort rate in a kilogram a day is that use 235 pure disappearing. And these are at this rate of the pure consumption, how long would the supply of the U235 last? And either effort rate is must be converted to the other form of energy by switching of the U235 in the reactor core. So the firstly we have to calculate for the efficiency. What is the station efficiency? So in this case, the thermal energy input is 3,400 megawatt, electrical energy output is 1,100 megawatt. So that we can calculate the efficiency. So A is the efficiency. So efficiency equation is useful output divided by energy input. Useful output divided by energy input. So useful output is 1,100 megawatt. Energy input is 3,400 megawatt. So by solving this one, you got 0.32 or 32%. So this is the nuclear energy. Okay, these are effort rates do the fission even organize the reactor core. So fission even is we can calculate I equals to P divided by Q. So power divided by the nuclear fission rate. So the power is output is 3,400 megawatt. Is coming out, so that is 3.4 into 10 power 9 joule per second. And divided by the fission rate is 200 mega electron volt per fission. Okay, this is multiplying with this is 1 mega electron volt is equal to the 1.6 into 10 power 13 minus 13 joule. So by solving this one, fission rate can be calculated. So 1.06 into 10 power 20 fission per second. So this is 1.1 into 10 power 20 fission per second. So this is what is nuclear fission rate. And another one is C. The F1 rates are in kilogram a day is a uranians are 235 fewer disappearing. So in this case are the uranians are how the uranians are 235 disappearing. So there will be 1 plus 0.25. So they multiply 1.06 into 10 power 20 atoms per second. So this is a 1.33 into 10 power 20 atoms. So this means that 1 is a here. We take it for 1.1 into the 10 power 20. Every substitution per second means every second 1.06 into 10 power 20 atoms is disappearing. So we also take that this is a fission. This is for the also we can take down for the efficiency. Because of it, not all the atoms are disappearing. Some atoms are their weight. Not all the atoms are useful. Some atoms will weight. So the weight will be around 25% weight. So the 1 plus 0.25 multiplied 1 by 0 into 10 power 20 atoms per second is disappearing. So there will be 1 by 33 into 10 power 20 atoms will be disappearing. Okay, so now this disappearing of those atoms, so we can calculate the day. How many kilogram per day? So then we can calculate the dm by dt. So this is for us 1.33 into 10 power 20 atoms per second. Multiply 3.9 into 10 power minus 25 kilogram per atom. So then, one atom is around 3.9 to 10 power minus 25 kilogram. So by solving this one, what you call is 5.19 into 10 power minus 5 kilogram per second. Okay, so every 6 seconds 5.19 to 10 power minus 5 kilogram of the uranium is disappearing. They are converted to the energy. So that 1 day, how many seconds? So 1 hour for the period of 300 seconds, multiplied 24. So that we can call it 1 day. So that 5.19 into 10 power minus 5, multiplied with 3,300 seconds, multiplied with 24 hour. So that is the mass so we calculate. In this case, 4.9 kilogram per day, 4.5 kilogram per day. So every day, we produce 4.5 kilograms of this uranium, so that it can produce 1100 megawatts energy output from this generator. So this is the way we can calculate the nuclear fuel consumption. And then, so at rate of the fuel consumption, how long would the fuel supply of the U235? So the U235 is that we can provide the 5.7 to 10 power 4 fuel rock. This is every day we can provide the 5.7 to 10 power 4 fuel. So we can calculate. So we can calculate so the day. So day can also be calculated. So the user 235U is 30%, 3% off. So this is for us 8.6 into the 10 power 4 kilogram. 8.6 into 10 power 4 kilogram. So here you see the uranium oxide. Uranium oxide is providing with the 8.6 to 10 power 4 kilogram of uranium. So 3% enriched. 3% enriched means that only the 3% of the uranium is provided to the energy. And therefore the 3% of 8.6 into the 10 power 4 kilogram can be calculated. So there will be 0.03 multiply 8.6 into 10 power 4 kilogram. Okay, so that this is the total supply of the uranium is 0.03 into 8.6 into 10 power 4 kilogram. So that every day is 4.5 kilogram per day. So that we can calculate the number of days. Day can be calculated 0.03 into 8.6 into 10 power 4 kilogram. Divided by 4.5 kilogram per day. So by serving this is about 570 days. So really I will 570 days we get. And now there's finally the E. F1 rate is must be converted to the other form of energy by switching of the uranium-235. So in this case the rate of the change can also be calculated. So that these are M by dt. the rate of the change, so that this is a dE by dt divided by the c squared. Because of the mt, E is equal to mt squared. E is equal to mt squared, so that E by c squared is equal to n. Therefore, the dm by dt is equal to d by dt E by c squared. So therefore, the dE by dt, we call this divided by c squared. So that in this case, the dE by dt is the energy by time, energy divided by time with this is the power. Power already we know. Output power is 3,400 megawatt. So that 3,400 multiplied 10 power 6 watt. Into 10 power 6 watt divided by c squared. C squared is the energy of the speed of the light. So the light is 3.8 into 10 power 10 squared. So by solving this one, dm by dt can be calculated 3.8 into 10 power minus 9 kilogram per second, or the 3.3 gram per day. So this is the ways the utilization or usage of the nuclear mass will be 313 gram per day. It's a nuclear fusion. Nuclear fusion is the binding energy for the nuclear energy shows that the nucleus combined to form as a nuclear combined to form as a single larger nucleus, the process called the nuclear fusion. So by combining the nuclear, it can form as a single larger nucleus. This is what we call the nuclear fusion. So the forms of various depend on the charge and the rigidity of the two interacting model. So two nucleus are colliding, so it can produce a nuclear fusion, and it can produce a larger nucleus. So in this case, we can write down the equation K equal to capital K equal to small k into T. So small k is the kinetic energy corresponding to the most appropriate speed, and multiply with the temperature, so you can get a K. So in this case, at the room temperature, K value is equal to 0.03 electron volt. So this is for the nuclear. So like I teach you that nuclear force, nuclear force and nuclear spinning, and also that we can calculate the nuclear energy produced by the force, and also I talk about the radioactive decay, and also there are two kinds of the radioactive decay, alpha decay and the beta decay. So I give you that for equation for the alpha and the beta decay and the radioactive dating. In the meantime, I also give you the nuclear model, the qualitative model and the combined model. So then the nuclear physics. So I also give you the energy released by the nuclear, and also the nuclear fission and the program for the nuclear fission, the fission the model, and also the principle of the nuclear reactor, nuclear control system, nuclear energy system, and this is the typical program to calculate the nuclear power and the nuclear pure calculation, and finally the nuclear fusion. So those are the all physics content. This is the last lesson, nuclear spin and the magnetism.